So let's look at another example, and I am going to go back and put arrows over my I and J because they are vectors. But once we've done this a few times and we get used to the idea that I and J are vectors, I'll probably stop putting that arrow over, more so out of habit. Now, the textbook's not going to always use the arrow. Some textbooks will do a bold to let you know it's a vector, and some textbooks will actually put the arrow on it. Let's talk about magnitude. How do we find the magnitude? Remember, magnitude is the length. And to find the magnitude, so let's say we're talking about this vector here, negative 5, 12. That's a position vector. That's going to be here. I want to find how long this vector is. Well, we could think about things in terms of the Pythagorean theorem. We know this side is 5 units, and it's 5 units to the left, so I'm going to use negative 5. And we know the height here is 12. So to find this arrow, which is the hypotenuse of the triangle, right, because we dropped it perpendicular, it would be the magnitude of V. Let's just call it C. It's going to be equal to negative 5 squared plus 12 squared. And that would be that length. Yeah, let me call it C. So I'll call this length C. So then C is going to be equal to the square root of that. So that's the square root of 169, which is 13. So we would say that the magnitude of V is equal to 13. All right, now let's come up with a formula for that. Let's say we have a vector, and I'll just draw this vector like this. I'll call it vector U. It has some point here that's a terminal point. I don't know what it is. Let's call it A and B. Well, this we could call A, right? Because that's the length along the x-axis, and this is the length along the y-axis, so let's call it B. So if we want to find this magnitude, then we could use our Pythagorean theorem to do it, just like we did in the last example with numbers. So we would say the length of this side squared, well, that would be the magnitude squared, is equal to A squared plus B squared. So if I want to get magnitude by itself, I would take the square root. So there's our formula for finding the magnitude of any vector. So let's try another one. Let's say we have the vector 6i plus 2j, and we want to find the magnitude. It's going to be the square root of 6 squared plus 2 squared, because that's our formula. So that's going to be the square root of 36 plus 4, which is the square root of 40. And then we want to break that down. 40 is 4 times 10. The square root of 4 is 2, so I can bring it out, and I can't do anything with the 10, so it stays under the radical. Now we can use that magnitude to help us find a unit vector. A unit vector is a vector that goes in the same direction as U, but it's going to have a length of 1, and we're going to force it to have a length of 1, because what we're going to do is we're going to take each component and we're going to multiply it by 1 over the magnitude. So I could actually think about this formula this way. So let's do an example. Suppose we have the vector 2, 1. So that vector, if I were to draw that, and this is a rough graph, would look like this. Has a terminal point at 2, 1. Let's find the magnitude of that vector. Magnitude is going to be square root of 2 squared plus 1 squared, which is the square root of 5. So my unit vector would be 1 over the square root of 5 times vector v. So I'm going to get 2 over the square root of 5, and I'm going to get 1 over the square root of 5. And if I were to rationalize that, multiply the top and bottom by square root of 5, so we get rid of square roots in the bottom, I end up with that. Now, if I'm graphing this, I need a decimal representation, right? Because I don't know what 2 over square root of 5 is if I were to try to graph it on here. So 2 divided by square root of 5 is about 0.89. And that second component is about 0.45. So if I were to graph that vector, 0.89, 0.45, it would look something like this. Okay, it's going in the same direction. It's just a smaller vector. Actually, I messed that up a little bit. 0.89 would be here, 0.45 would be here. So see how it's going in the same direction, right on top of? That's always going to happen. It's going to be right on top of that other vector. It's just not going to be as long necessarily as that other vector. So let's show that u has a magnitude of 1. How can we show that? And we can show that by finding that magnitude. So the magnitude of u is going to be the square root of a squared plus b squared. So I'm going to take 2 square root of 5 over 5, and I'm going to square it. And I'm going to take the square root of 5 over 5, and I'm going to square it. I'm going to add those together and then take the square root. So we have to be careful when we do this. So I'm going to square each of the top pieces and the bottom separately. 2 squared is 4. Square root of 5 squared is 5. 5 squared is 25. Square root of 5 squared is 5. 5 squared is 25. So now I've got 20 over 25 plus 5 over 25, which is 25 over 25, which is 1, and the square root of 1 is 1. So you can see how that does have a magnitude of 1. So now we're going to start getting into some physics applications. If we want to find a vector from direction and magnitude, a vector is going to represent speed in the direction of an object, then in physics, we're going to call that a velocity vector. Okay, velocity has both speed and direction. So it tells us how fast it's going and in what direction it's going. If a vector represents direction of the amount of force acting on an object, it's called a force vector. And we can talk about the coordinates of the terminal point in terms of sine and cosine. So we have this position vector v. We could think about this theta value, right? And I'll just call it alpha to be consistent here. If I know that alpha value, then I can think about the coordinates in terms of what would it be in terms of that angle from the positive x-axis. And that's where I'm thinking about that x coordinate and that y coordinate. So I can write that in terms of my I and j vectors. And this is always going to be a unit vector. it doesn't matter what the length of that vector is going to be, but if we force it to be 1, then it's going to make it a little easier for us to think about. So then vector v is going to be the magnitude of v times that vector u, which is written in terms of sine and cosine. Forces are going to combine the same way that vectors add. So if we want to know what the force is when we have two objects acting on something. So let's say we've got a stump and we are trying to remove a tree stump and we have two tractors that are pulling on that tree stump. Well, those are two different forces acting probably in two different directions. They're not going to be riding side by side. They're probably going to be acting on an angle on that tree stump. So we can figure out the force being applied to that tree stump with those tractors by adding the force of the two vectors together. All right, so let's look at a few physics examples. So in this example, we have a man that's pushing this wheelbarrow up an incline that's at 20 degrees. And then we know the weight of this is 100 pounds. We want to express the force vector in terms of I and J. So we could think about that vector that's acting along that incline there in terms of cosine of 20 degrees and sine of 20 degrees. When we apply the force that's being acted on that's 100 pounds, okay? And that pound has to do with weight of gravity and all that fun stuff from physics. That's the magnitude. And if we wanted to, we could write that as cosine of 20 degrees I plus sine of 20 degrees J. Okay, they're wanting it in terms of I and J, so this is the notation I would use. We could use this as a shortcut notation, but they both mean the same thing. This is the force acting along the path, so that's the vector that's being described here. And that is a unit vector. If we take this squared plus this squared, we know sine squared plus cosine squared is equal to 1. So then that length would have a magnitude of 1, because the square root of 1 is 1. And we're just really just thinking about what that force is along that unit vector. It doesn't really matter how long the ramp is, because remember when we talked about unit vectors, a unit vector is in the same direction as the original vector. So it doesn't matter whether that ramp is a foot long or whether it's 100 feet long. We can express that path that way.